We should start, Christiane. And so next talk is by Christiane Tretter, University of Bern, and she will talk about challenges for non-self-adjoint spectral problems in analysis and computation. So please start.
Let me first try to get this full screen again. Yeah, thank you very much, Ricardo, and thank you all the organizers very much for giving me the chance to speak in this nice meeting. The combination of analysis and mathematical physics and also numerical analysis has always been a very important aspect in my research. And for my favorite type of problems, namely non-self-adjoint problems, it's also indispensable that these various fields interact. So my field is spectral analysis in particular. So here the reason is simply that it is very difficult to obtain reliable information on the spectrum for at least two reasons. So first of all, the spectrum is in general unstable under perturbations, and it's not so difficult to understand why. So let's imagine that we have a self-adjoint operator A perturbed by a bounded operator B, and lambda is not in the spectrum of A. Then we can extract the bijective A minus lambda, for example, to the right, and then we see that the bijectivity of the left-hand side depends entirely on the bijectivity of this term, and so a simple Neumann series argument tells you if this norm is less than 1, then lambda is not in the spectrum of A plus B. Now, if A is self-adjoint, the norm of the resolvent is entirely controlled by the distance to the spectrum of A, and hence it follows that the perturbed spectrum is in a norm B neighborhood of the spectrum of A. So small perturbations cause small changes in the spectrum. Now, this connection to the spectrum is lost when you give up the assumption that A is non-self-adjoint. Because, in general, for a non-self-adjoint operator, the resolvent norm is only controlled by the distance of this point lambda to the numerical range of A, and this can be a much larger set than the spectrum. So the same Neumann series argument only tells you that the perturbed spectrum lies in a norm B neighborhood of the numerical range of A, right? So if you just think of A being a 2 by 2 matrix Jordan block at 0, then the spectrum of A clearly is just 0, but the numerical range is a disk of radius 1/2 around the point 0. So this is a much, much worse bound that you get from here. So this is one thing. The second thing arises when you want to approximate eigenvalues or spectra more generally. Such spectral approximations are prone to two different defects. So let's assume we have an unbounded linear operator T, and we want to approximate it by a sequence Tn, which is obtained, for example, by domain truncation or finite sections. In this case, the first unwanted phenomenon that you may have to face is spectral pollution. This means that there may exist a sequence of eigenvalues lambda n of your approximating Tn, having an accumulation point lambda, but that lambda is not a true spectral point. You would also call that a spurious spectral point, a spurious eigenvalue. So this is one effect. There's a nice survey paper about spectral pollution by Lionel Boulton, for example, if you want to know more about that, but we'll come back to this also later in the talk. The second unwanted effect I call spectral invisibility. This means that there may exist true spectral points lambda that are not obtained as limits of your approximation sequence, so there are no accumulation points of some eigenvalues of your approximating operators. So these are very unwanted phenomena, and unfortunately, they are not just restricted to theory. And in the following two examples, I would like to show you that they may already occur for relatively simple examples. So the first such alarming example is the right shift in L2 of Z. This is our T, the matrix representation in L2 of Z. Now we take finite sections. Then these Tn clearly look like that, n by n matrices. And then it's well known that the spectrum of the right shift is the unit circle in L2Z. But clearly the spectrum of the Tn consists of an n-fold eigenvalue at 0. So this is looking very bad, actually, because no point of the spectrum is approximated and 0 is a spurious eigenvalue. So we have complete spectral invisibility and spectral pollution at the same time. Now, again, unfortunately, the spectral pollution is not even restricted to non-self-adjoint operators. The right shift is, of course, a prototype of a non-self-adjoint operator. Spectral pollution may even occur for self-adjoint problems. And this is our next example. So this is a diagonal matrix with plus minus 1, plus minus 2, and so on the diagonal. And now in L2n, and now we look at two different approximations. The first one, maybe most obvious one, is that you take finite sections after 2n elements here. So you project onto the first 2n unit vectors. Then clearly you get these points as eigenvalues of your Tn. And in the limit, when n tends to infinity, you get all the eigenvalues and you get no spurious eigenvalues. So there is complete spectral visibility and no spectral pollution. That's fine. But if you change the spaces and take, say, the space Hn minus 1 from up there, but then you take a linear combination of xn of the unit vectors, basis vectors e to n minus 1 and e to n, combined by some factors that I will determine later and restrict the Tn to this subspace. And then we take an arbitrary point lambda that is not a spectral point, so not in this set of the integers. And then we can choose theta n in a very particular way, like this, and then compute that the lambda n, when you apply Tn tilde to this xn up here, this is an approximating eigenvalue then of your approximating operator. And you can check that the lambda n are given by this formula here with this theta n, and that tends to lambda. So for this approximation, we have that every point on the real line that is not a true spectral point can occur as a point of spectral pollution. So every such lambda is a spurious eigenvalue for some approximating sequence T and delta. Just recall, this was a self-adjoint operator T. So we will come back to this example again later in the talk. Now, what I would like to show you now in my presentation is, first, I want to present you an operator theoretic tool, which allows you to kind of assess and control these unwanted effects. And then in the second part, I would like to show you several applications to, in fact, from mathematical physics. So this tool I want to show you is the so-called essential numerical range. So for this, we need a Hilbert space and just some unbounded linear operator. There are no further assumptions than just that. Well, of course, the numerical range itself is a well-known concept. Here it is again. So it's the set of all scalar products Txx, where x is a unit element in the domain of T. It's well known by the Toeplitz-Hausdorff theorem that this is a convex set in C. And it has the so-called spectral inclusion property, which means it contains all the eigenvalues. And its closure contains, in general, the approximate point spectrum. So if you want to have inclusion of the full spectrum in the unbounded case, you have to require that the dimension of the range, the codimension of the range, is kind of pressed down to 0. And so you have to assume that each of the at most 2 components, due to convexity, at most 2, of the complement of the numerical range's closure, that they have non-empty intersection with the resolvent set. That's always true for bounded operators. So for bounded operators, you always have this. Now, the essential numerical range is a concept of numerical range that allows you to enclose the essential spectrum. I'll come back to that. Because there is not the essential spectrum for unbounded, for non-self-adjoint operators, but let's first define it. So the essential numerical range is the set of all lambda in the complex plane, such that there exists a sequence xn of normalized elements tending weakly to 0, such that the scalar products Txn, xn tend to lambda. So this set was first introduced long ago, 68, 62, by Fillmore, Stumpley, and Williams for bounded operators. And somehow it remained untouched for like 5 decades. So when we started to consider it, maybe around 6, 7 years ago, we also understood why. Because for unbounded T, this type of concept offers quite some challenges and a lot of surprises. And so the paper that we wrote on this joint work with Sabine Böckli and Marco Maletta appeared in 2020. So let's first start with some simple properties of this set that do carry over from the bounded case to the unbounded case. So the first thing that you see from here is that clearly this set W of T will be a subset of the closure of the numerical range. All these things here are in the numerical range, so we have limits, it lies in the closure. So this is the first property. Then you can show that, like the numerical range, WE of T is convex, but it's closed. This is different from the numerical range. You can also show that it contains the essential spectrum, number 2, I should add, and hence the convex hull of this essential spectrum. because for non-self-adjoint operators, there are in the Hilbert space at least 5 different essential spectra, and they can really be different. So here I talk about this number 2 in Edmonds and Evans, the one defined with singular sequences. So the first part of this definition is absolutely the same as for the essential numerical range, but here we require that the norm of t minus lambda xn tends to 0. Right? So by Cauchy-Schwarz inequality, it's then obvious that this inclusion will hold, right? Now, the first difference to the unbounded case is that while in the bounded case, WE of t is always non-empty, this is no longer true if t is unbounded. We can say a bit more here because we proved a number of geometric properties of this WE of t. Let me show them maybe all together. So if W of t is a line or its closure a strip or the whole plane, in all these 3 cases, the essential numerical range is indeed also non-empty, and it has the same geometric form. It's either also a line and hence equal to the numerical range, also a strip, possibly smaller, or also the entire plane. The half-plane case of W of t is different, because in this case, we have to require that WE of t is non-empty in order to be able to conclude that WE of t is a half-plane. And indeed, there is an example that this can be empty in the case of a half-plane. So we take, for example, such a diagonal infinite matrix in L to N0. So these eigenvalues here, they lie on some sort of parabola in the right half plane. And so the numerical range's closure is the closed right half plane, but you can show that WE of t is empty because this operator has compact resolvent is a little bit in the background. So this is a case that really this cannot be improved. We can't omit this assumption. Now, on this slide, you might maybe have 2 questions. So the first question is, well, sometimes you know that in the case of the spectrum, if your operator is self-adjoint or normal, then the numerical range is the convex hull of the spectrum. So is this maybe also true for the essential numerical range, that for a self-adjoint or normal T, we have in fact equality here? This is one question. And then there is another question, maybe is this always true that in such a situation here, if your operator has compact resolvent, that WE of t is empty. So I mentioned it already, but is it really true in general? That's another question. Well, let's first start with whether we could have equality here for normal t. Well, for bounded t, there is a result of Salinas from 72 that even for hyponormal t, this means this property here, that t star t minus t star is non-negative, then indeed W of t is the convex hull of the essential spectrum. But this is no longer true again for unbounded t, not even if t is self-adjoint. And here is the problem. So we need a concept, the so-called extended essential spectrum here, because as we shall see, operators that are not semi-bounded are a bit dangerous. So the so-called extended essential spectrum was already introduced earlier by Levitin-Szargorodsky, and it's just the same as the essential spectrum if T is bounded. And if say it's sigma E of T with 1 or 2 points added, minus infinity, and or plus infinity, depending on whether t is unbounded from below and or above. So in the worst case, you have to add 2 points. And it turns out that if t is self-adjoint, then W of t is the convex hull of the extended essential spectrum minus these 2 points, again, because this is a subset of the complex plane. Now, what's the difference here? Well, let's look at this example that we saw on the second slide, the second alarming example, this diagonal matrix here, infinite matrix. Well, it has compact resolvent. So sigma E of t is empty, but the operator is unbounded from either side. So in this extended essential spectrum, we have to add the points plus and minus infinity to the empty set. And now you see what happens when you take the convex hulls. Well, here in the essential spectrum, it remains empty. But here, you have to add the entire real line for the convex hull. And then if you take off these 2 points, WE of t remains the whole real line. And the fact that this is the whole real line is closely related to this unwanted phenomenon that the real line, apart from the spectrum, is full of spurious eigenvalues, if you choose the right approximations. Right. Okay, so in fact, some of the properties that you see on this slide and also on the previous slide were not proved by means of the original definition of this WE of t I showed you. In fact, in the bounded case, there are 5 different and all equivalent characterizations of this WE of t that can be useful here and in other proofs. But again, unfortunately, not all of them remain equivalent in the unbounded case, and not all of them were easy to generalize. And this is why another name comes into play here. This is my present PhD student. He will finish very soon. So with him, we solved the most difficult, in the end, remaining problem of the WE5. But let me slowly take you through these definitions. I will point you to the important points. So the first 3 of these WEIs, these new notions of essential numerical ranges, are all intersections over certain numerical ranges and their closures. So in the first case, you restrict your T to finite codimensional subspaces. So the V has finite dimension and you restrict to V orthogonal. For the second type of set, you add finite rank K and take the intersection. For the third one, you add compact K. For the fourth one, instead of an arbitrary weakly to 0 convergent sequence, you take an orthonormal sequence. So that's a special convergence, weak convergence to 0 to get your convergence to lambda. And now this WE5, there the main problem, I mean, these definitions were relatively easy to generalize, but the WE5 was a real problem already to find how to write down this set. So I won't say much about it because it's a bit too complicated, but you compress somehow your operator to certain infinite dimensional subspaces, and then you take the M and its orthogonal complement and you check for which lambda is this compact. And so that is very counterintuitive, I think, this definition. In any case, in the bounded case, all these sets agree with the set WE of t I showed you at the very beginning. Here, in general, without any further assumptions on the t, it's just an unbounded linear operator, we still get 2 inequalities. So WE2, WE3, they are equal to the original WE. But already this WE4 with this orthonormality gets only an inclusion here. Then next is the WE1, and then the possibly smallest is the WE5. I mean, these numbers were given in the bounded case. This is why it didn't play a role in what order they appeared. But here, of course, one would have liked another enumeration. Anyway, that's how it is. Now, in the next few lines, you will now see gradually under what assumptions an equality appears further down. So the next equality with WE of E4 appears if you assume that your operator is densely defined. The next equality here appears if the domain of T intersected with domain of T star is dense, or if the numeric range is not the whole plane. Now, if you want to get the last one, you have to go even one step further. You have to require that this set here is also a core of T. Then all are equal. Now, this set here somehow is, let me go back one page. So especially in this statement here, I really started to wonder, maybe one of these things will always hold, and then they are always equal if your operator is densely defined. And I tried to show this. And then, of course, you get to this point that you need to know properties of this set here. And I thought definitely something must be known here about this intersection. But in fact, it wasn't. And so I got in touch with my colleague Yuri Alinsky, and we then started a collaboration on this. And I'll not talk about that today. I will just tell you the title and show you a funny picture that I borrowed from another talk with the kind permission of Dwight Barclay. So in fact, for this domain intersection, you can have everything from being empty to being a core and everything in between. Every finite dimension, every finite codimension, really all the cases. And the amazing thing is you can have that for very nice operators, for example, for M-sectorial operators. So this was really a surprise. And the theorem had to remain as it was because, I mean, this was really an assumption we needed. But as I said, I will not talk about this. I will tell you one more property of these sets because we will need it later for the applications. So stability results, we saw already some in the first talk by Fritz. For the essential spectrum, it's well known that the essential spectrum, especially in the self-adjoint case, is stable under compact and perturbations. And also in the non-self-adjoint case, for most of the concepts. Here, we can show the same, and we can show the stability also if the sets are not equal. So any of these concepts is stable with respect to compact perturbations, even if they are not the same, the sets. Now, in the essential spectrum case, we know that we might also be able to admit relatively compact perturbations. And again, disappointment here. If we try that and take the intersection not just over compact, but over the compact, over the T compact, then of course, because compact is T compact, we get an inclusion in here. But in general, these sets are not the same, right? So you need some additional assumptions, and I will be very brief here. So in fact, this inequality is possible even again for self-adjoint T. Here is an example. If you have a self-adjoint T that is not semi-bounded with compact resolvent, then the W of T, the WE, and hence the WE3 is equal to the real line, but this other set is empty.
Sorry, can I ask a quick question?
Yes.
This numbering 1 to 5, is it somehow parallel to the numbering of the essential spectral definition?
Oh, no. Unfortunately, also not. So it's neither suitable for the unbounded case, and unfortunately, it has nothing to do with this numbering of the essential spectra.
Thank you.
That's really a pity, I have to say. It's extremely confusing, I think. But it's a good question, yes, because you could think it is. Because it's also 5, that's even more
Right,
misleading,
exactly.
I think. Yeah.
And I
right.
don't remember 5 definitions of essential spectrum by heart. So it's
it's all with these Fredholm properties. So one basic reference for that is the Edmonds-Evans book on spectral theory and differential operators. And Fredholm just being not Fredholm or being not Fredholm and so on. So there are even more than just these 5, I have to say. And in the Banach space case, even more, but unfortunately not related to our numbering here.
Thank you. Thank you.
Thanks for the question. That's a good point. Okay, so this was this new set. Under some assumptions, for example, the assumption that T is self-adjoint and you have a K that is symmetric, then if it's T compact, then indeed they are the same. And there is more, I will not comment much about this theorem. There is more variety of such results when you get stability with respect to relatively compact perturbations. But these results, maybe just one word here, require that you can decompose your operators into real and imaginary parts in operator sense at this point, right? And this is by no means something automatic. For bounded operators, again, yes. But in any case, if you have that, then you can still get some stability with respect to relatively compact. I mean, results of this kind are, of course, useful when you want to apply such things to differential operators. This is why I decided to show them. But I would now like to concentrate really on this spectral convergence problem. So what I would like to show you in the next part of the talk is what this essential numerical range can help you when you want to assess safety of spectral convergence. Let's put it that way. So I will show you, I mean, our results are really very general, I have to say that. So they apply simultaneously to projection methods and domain truncation methods, but I will treat them separately here because the assumptions are a bit different. So let's first start with the projection method. So this means we take a sequence of finite dimensional subspaces of our Hilbert space in the domain of our operator, and we denote by PHN the corresponding orthogonal projections. And then we compress our operator T to these HN. We will later assume that these PHN converge to the identity so that we get some convergence to the T. But of course, we have unbounded operators and we have to specify what we mean by convergence here. So now I will show you our first main result on spectral convergence. Here we now assume that T is a closed operator and densely defined, but that's all. If these projections to our subspaces tend to the identity operator strongly, and if the Tn tend to our T in so-called generalized strong resolvent sense, this means the following, that you have to have a point lambda 0 in all the resolvent sets, such that the resolvents in lambda 0 of the Tn tend strongly to the resolvent of T. In this case, spurious eigenvalues may only occur in the essential numerical range of T. And secondly, every isolated spectral point outside the essential numerical range is indeed being approximated. So there exists a sequence lambda n in the spectrum of your approximating sequence tending to this lambda. So this is a very satisfactory result in some sense, and it's even in a special sense optimal, because you can show that for every point lambda in the essential numeric range that is not a spectral point, there exists a projection method for which this lambda is a spurious eigenvalue, right? So if you compare this to earlier results, let's maybe first comment on this. There were results of this kind, maybe not the optimality, but for bounded T by Declou already back in 81. The essential numerical range existed already. Other results by Levitin, Chargorodsky, and Levin-Serre, they did not have to use the essential numerical range because they considered only self-adjoint operators, and they could work with the convex hull of the extended essential spectrum that I told you before, happens to be the essential numerical range as we now know. So the bottom line of this slide is, and maybe also one bottom line of my talk, this essential numerical range is indeed the smallest possible set capturing spectral pollution for projection methods, right? Now for domain truncation method, we have a very similar result. So this theorem 7 can also be made applicable to domain truncation methods. Let me tell you a bit more about the setting here. So in this case, we assume that we have some bounded, some domain omega in Rn, or Rd, I called it here, and then some nested sets omega n exhausting this omega, and we consider a strongly elliptic partial differential operator T. Sorry, here omega is even Rd. Yeah, so in this case I took Rd, yes. So they exhaust Rd, and the Tn's are the restrictions to this omega n. So we assume that they are all induced by these sectorial forms here, where the coefficients, capital Q alpha beta, are L infinity functions, complex valued on Rd, and the leading coefficients are constant, right? So this is the assumption here. The P2M is the principal symbol then with these constant coefficients here. Now the difference, it's not completely finished, the statement yet. Theorem 7, the same statements hold, but here we need one additional assumption. The generalized strong resolvent convergence is not enough for Tn to T, but we also need it for the adjoints in this case. Right? Okay, now of course the practical question is very nice, but how do we get hold of this essential numerical range if we have concrete operators? So let me show you one example here. So let's assume that the coefficients, not just the leading ones, but also the other ones, that they at least have limits when x tends to infinity, say C alpha beta. Then we have a so-called limiting symbol, P infinity. This is the principal symbol, and then these limits from the lower order terms. And then one can show, because you can boil down everything to the symbol level somehow, and the symbol level is a multiplication operator level. It turns out that WE of T is the convex hull of the range of P infinity. And this is just the convex hull of the essential spectrum of T in this case, right? Because of course the symbol is then a normal operator, so you get this. Okay, so in such a case, we can compute the essential numerical range. And now I would like to show you one application, really with the domain truncation, then also what you can get from this theorem 7 for a concrete example. So this is an advection diffusion type differential operator in one dimension. So we have two coefficients, Q1 and Q0 here. L infinity, complex valued, we assume that the Q1 tends to -2 and Q0 tends to 0. This is an example that was considered earlier, for example, by Brian Davies. And so we know already something here. For example, we know that the essential spectrum is this parabola in the right half plane. Now we can then show from what we learned just on the previous slide, we have this limiting situation that the essential numerical range is the convex hull. So the whole parabola gets filled for the, you will see a picture in a minute. And now we do, here it is already. Here, now we do the following. I want to show you now some truncations and the spectra. So let's assume for simplicity that the Q1 is just equal to -2. And for the Q0, we take such a function here tending to 0 at infinity. Now we truncate our real line into intervals omega n, say symmetric around 0. And so here, for example, it's called omega n. And on this picture, the interval is -9, 9. And so the blue dots are the eigenvalues that you get on this truncated interval. So you get a bunch of eigenvalues here on the real line, and then some eigenvalue in the other half plane, right? Okay, now we want to increase the n and make it larger and larger and see what happens with these eigenvalues. Well, it turns out these eigenvalues will always be real here, and they will always stay on the real line inside the parabola, and this one here will stay out. So the picture is like that. These are the ones inside the parabola. This is the one in the left half plane, in the limit when the interval length tends to infinity. So our theorem now tells you the following. These eigenvalues here in the right half plane, they lie inside of the parabola, which is the essential numerical range. So they may be spurious eigenvalues because they lie inside. It turns out they indeed are spurious eigenvalues, but that doesn't follow from our theorem. It just tells you here you have to be careful, because there are no eigenvalues on the real line one can show separately. However, this eigenvalue here, that it has a limit, the eigenvalues when Sn tends to infinity, this lies not in the essential numerical range, and hence, by our theorem, the limit must be a true eigenvalue. So that's what our theorem guarantees you. So these are all spurious eigenvalues. You know that they are prone to be spurious by our theorem, that they are spurious you show separately, and that this is a true eigenvalue follows from our theorem. Now, towards the end of my talk, I would like to show you a more challenging application, namely domain truncation for Maxwell's equation. So, and this is Maxwell's equation in a non-self-adjoint variation. So we consider in this case an omega in R3 with Lipschitz boundary and some nested omega n exhausting this omega, and we consider always simultaneously the original problem and the truncated problems. Now, this is the system, the Maxwell system. The functions E and H are the two components. And we have a boundary condition on the component E here. And the functions epsilon, mu, and sigma are matrix valued, real 3×3 matrix valued, L infinity functions. And the sigma is the conductivity, and this is in front up here. The assumptions are that epsilon mu are strictly positive as matrix functions, and the sigma is non-negative, right? So these are the assumptions. Now, let's have a look at this problem in operator matrix form, because the structure becomes much better visible here. So in fact, it's not a classical spectral problem because we have these additional epsilon and mu next to the spectral parameter, but it's not difficult. They are boundedly invertible, so that's not a big deal here to get get them away. Now this side here, we have the curl operators here, and here I was a bit more precise because it's not curl and curl. This is curl 0. This is the adjoint operator really of the curl here, because we have this boundary condition. Now the problem is this sigma here, right? Because the sigma appears here, and you see while these corners are adjoint to each other, you know, like for a Dirac operator, this, as long as the sigma is 0, this is self-adjoint. But as soon as the sigma is there, you have the non-self-adjointness through this corner here. Now, one of my favorite things to do before you start to do numerics, I think it's always a good idea to derive some abstract spectral enclosures. Because if you know where the spectrum is, then you already know where to look, because outside your spectral enclosure, there can be nothing. And that's what we first did here. And this is our result. I will show you the same, some illustrations on the next slide immediately, and I will just point you to some details here. So the spectrum of this Maxwell pencil, first of all, lies in the following union of sets. So here is a bounded interval on the negative imaginary axis below 0, and it's determined by the maximal spectral point of this sigma multiplication operator and the minimal of this epsilon function here, right? These are all physical quantities, right? They are known. So that's an imaginary interval. Then here we have a horizontal strip below the real axis, and this has just half the width of this interval. Right? So this is this yellow set. It will always appear later on in yellow. Then some additional inequality can be proved, which gives you something when this lambda min omega, which is basically the minimal spectral point of the curl 0, if this is positive, then this gives you really an additional restriction that I will then show you on the pictures. Now, we do not only prove spectral enclosures. Outside of this yellow set, we also prove resolvent estimates. And now I will show you what happens. So if lambda min omega is 0, we just get this yellow set here. If it starts to grow, there are two thresholds where the enclosure through this inequality here changes. So as soon as this first eigenvalue of the curl 0 gets positive, you cut out some region here around 0. This is the imaginary interval. This is the horizontal strip of half the width. Now, if this grows further beyond this threshold here, all in these physical quantities, another part gets cut out here, and this gets larger. Now, you can imagine when this starts to grow even further, now the factor is 1/3, it splits off from this imaginary interval, right? So that's quite an important thing, because then you can already see that there can be no eigenvalue accumulation, for example, of at this part of the spectrum. This follows from our result. Okay, so now this is the picture for the resolvent estimate. I didn't write down the formulas. So this again, this yellow set, and then you see this is a much nicer picture for the resolvent norm level sets. The numerical range, by the way, of this pencil would be this entire strip. So you couldn't even get to this region, for example. Now, also important for numerics is the essential spectrum, because essential spectrum is always dangerous for numerics. So we determined the essential spectrum in the following case, when these matrix functions have limits of the form multiple times identity matrix. So in this case, epsilon infinity and mu infinity for these two, and for the conductivity, we assume that the limit is 0. It turns out that the essential spectrum of this big Maxwell problem is closely related to the essential spectrum of this quadratic pencil L infinity, it's not a difficult quadratic pencil because only omega squared appears, right? So that's, I mean, there is no omega here. It's actually a multiple of the first Schur complement of this Maxwell pencil, but that's not important for the following. I will skip details about the domains because, of course, they have to be carefully specified here. Now, what turns out is that the essential spectrum of our Maxwell pencil on the real line is given by the essential spectrum of this L infinity operator polynomial. And on the imaginary axis, we just get the information. It's in this interval, namely this interval that we knew before. The spectrum can only be there. So this doesn't give more on the imaginary axis, but it shows that there is no essential spectrum, for example, in these areas here. It's confined to the real line because L infinity, in fact, you just have to take the square root of the essential spectrum, basically of this curl zero operator multiplied by these numbers here. So you can precisely describe how the essential spectrum looks on the real axis. Okay, and now what about the truncations? And this is going to be the last slide. So a similar quantity as before appears. Before we have this lambda min omega. Again, the curl zero appears, but now the essential spectrum of it. Before we had just the spectrum. We can now show for this Maxwell pencil and its approximations Vn that the set of spectral pollution, I abbreviated it like that here, is contained in the essential numeric range of this reduced pencil L infinity. And this is in fact combined out of these two intervals on the real axis. Right? And so here, this WEL infinity is not precisely, I mean, the L infinity is not an operator, it's an operator polynomial. So you, strictly speaking, you have to define it. It's the set of all omega in C such that 0 is in the essential numeric range of this fixed operator here, right? So again, the essential numerical range comes into play here. And the second part, again, a bit similar to the abstract results. Every isolated eigenvalue of the Maxwell pencil outside of first this set here on the real axis and this imaginary interval is indeed approximated by the domain truncation of this Maxwell pencil. And I think the pictures say much more here. This is for a particular example now. So we have omega is this waveguide here. So we have like a rectangle, then times this infinite semi-interval here. And what we do now is we truncate this infinite part at n, call it omega n. And now in this example, we have just set epsilon and mu to the identity matrix in R3 times 3, and sigma is 1 on this, say, omega 1, for example, here, and otherwise 0. And here you see in the first picture the true essential spectrum in this case. So it's we obtained that it's the square root of this curl 0, which is in this case these two intervals here. And then on the imaginary axis, you can work out, but that's an extra work. We know it's on this imaginary interval, but in fact, it's just 3 points, right? So it's these 3 points here. Now, when you do the domain truncation, you see a picture here for n equal to 50. You see a lot of eigenvalues accumulating here near the real axis. And then some branches of eigenvalues that we had already here for the true problem, right? And so our result tells you that indeed these limits do approximate true eigenvalues because the pollution is only contained on the real line in these two basically red intervals, right? So this example tells two things. First of all, our result also gives something new in the self-adjoint case, because before one did not know that there is no spectral pollution to the left and to the right of 0 in these spectral gaps, because spectral gaps are always prone to spectral pollution, as we saw earlier. This is the first thing. The second thing is that you see from here that our estimate of the spectral enclosure is sharp. So the whole imaginary interval is occupied down to the bottom point. And these branches, they tend in the limit to the boundary of our spectral enclosing set. So this was a quite nice application, and also I have to say a bit challenging. In this last part on the Maxwell equation, you will see on the next slide, there was another person involved, namely my and Marco's previous postdoc, Francesco Ferraresso. And this is also the works on which my talk was based. And I think I should stop at this point. And thank you very much for your attention.
For this beautiful talk, illuminating talk, are there any questions? Well, I have a question. At the beginning of your talk, you mentioned also this invisibility problem. So eigenvalues you could not see. Do you have some results concerning invisibility, general methods when it appears, will not appear?
No, not at this point. I mean, we have this example that I showed you. So here, for example, but no, we don't have results on that at the moment. It's maybe also a bit difficult, I would say, right?
Well, okay,
Yeah.
thank you. Any other question? Well, then if you take some typical quantum mechanical problems, say Yukawa potential or Coulomb potential, how do these spectral pollution issues manifest in those cases? So
Well, whenever you have, for example, gaps in the essential spectrum or so, you are in danger at the moment. So we are just about to, it's not yet finished, complete work on essential spectra, essential numerical ranges for Schrödinger operators, because this is, of course, a particularly important class. And there are some more special effects and even more concepts of essential numerical range you could think of. And so, of course, the main point is really, and that's why we started to consider these concrete operators, what can you really say about the shape of these essential numerical ranges, right? But I mean, you could try to do this truncation, maybe we haven't tried it around singularities, but that's certainly possible too.
Well, okay, well, thank you. Is there any other question or comment or? Well, otherwise we thank Christiane again for her beautiful talk.
Thank you.
Then we meet tomorrow at 9. And for those who have not joined before, let me remind you that you can listen to the talks in the YouTube and Facebook channels of IMAS. You got the login when I received information in how to join the Zoom session as well. Okay, so as always, it's 9 Mexico City time. Well, nice to see all of you, and then thanks again, Christiane.
Thank you.
So we keep in touch. We see each other tomorrow. Yeah.
Ricardo, can I ask you a question?
Yes.
Because I wasn't there at the very beginning. I don't know if you said something about it. What is this beautiful, this beautiful. Is it a building that gets mirrored in the water?
Oh, well, this is the library. This is, you know, this is, UNAM is a World Heritage Site. And this is our library that has a famous mural. And
Yeah,
then
it's
this,
fantastic.
well, the pond there and it's reflected in the pond, yes.
Yeah,
This is
beautiful.
the part of the campus which is UNESCO World Heritage.
Oh,
So
great.
yes,
It really looks very nice.
Well, thank you. Right.
Okay.
Well,
So
maybe.